A radio command leaving Earth right now will not reach our most distant working spacecraft for almost a full day. Speak to it, and your sentence arrives tomorrow. This is the first thing distance steals. Conversation. Go farther, and it takes more. Between the stars, it steals your lifetime. Across the galaxy, it steals your civilization. And at the largest scales, space itself stretches faster than light can cross it, stealing the destination entirely. The universe is not frightening simply because it is vast. It is frightening because every step outward quietly removes something you assumed you had. A reply, a rescue, a shared moment, a place you could one day arrive. Distance is not emptiness. Distance is subtraction. And the further out we look, the more it quietly takes. If that idea unsettles you the way it unsettles me, do me a small favor and hit like and subscribe. It quietly helps this little channel more than you'd think. Now, settle in and get yourself comfortable. Let's begin. Somewhere inside a control room in Southern California, an engineer types a short string of commands, checks it twice, and presses send. Then she does something that would look absurd in almost any other profession on Earth. She waits. Not for a second. Not for an hour. She settles in to wait the better part of 2 days. The command is on its way to Voyager 1, the most distant working machine our species has ever built. Right now, that spacecraft is roughly 25 billion kilometers away, about 16 billion miles drifting through the dark, beyond every planet, beyond the edge of the sun's magnetic bubble, out in true interstellar space. Its radio signal is not slow. It travels at the speed of light, the fastest anything in this universe is allowed to move, 300,000 kilometers every single second. And even at that impossible speed, the message needs around 23.5 hours just to arrive. If the spacecraft answers, that reply takes another 23.5 hours to come home. So when an engineer says good morning to Voyager 1 on a Monday, the spacecraft's good morning does not return until Wednesday. A simple yes or no question becomes a 2-day exchange. There is no conversation here. There cannot be. By the time you learn how the spacecraft reacted to your last instruction, the instruction is already a full day in its past, and the spacecraft has been alone with the consequences the entire time. This is the first thing distance takes from us, long before space becomes truly enormous. It takes the reply, the back and forth that every human relationship, every rescue, every act of teamwork quietly depends on. We almost never notice that dependence, because here on the ground a reply is instant. You speak, and the answer comes back before you have finished breathing. Push outward into the solar system though, and that instant reply begins to stretch, then crack, then break entirely. And once it breaks, everything we assume about being able to help, to fix, to save, breaks along with it. Consider what Voyager 1 has lived through recently. In late 2023, the spacecraft began sending home a stream of meaningless data, the same pattern repeating over and over, a kind of digital stammer. Something in its aging computer had failed. The team that built careers around this probe suddenly faced a patient that could only be examined across a gap of light hours, with every test taking days to complete. Send a diagnostic. Wait a day for it to arrive. Wait while the spacecraft acts on it. Wait another day for the result to crawl back. Check the result. Think. Try again. A problem that an engineer could have chased down in an afternoon if the hardware sat on a workbench took months to solve from 25 billion kilometers away. They did solve it, but they solved it the way you would defuse a bomb while wearing a blindfold and reading the manual through the mail. It became harder still in 2025. The single giant antenna, capable of sending commands to both Voyager spacecraft, a 70-meter dish called Deep Space Station 43 in Canberra, Australia, went offline for most of a year for critical upgrades. Before it went dark, engineers had to scramble to wake up a set of backup thrusters that had been dormant for decades, because if those thrusters failed during the blackout, there would be no way to send the fix in time. Think about the strangeness of that. A machine you cannot reach for months, that can only be commanded by one dish on one continent, that answers questions a day late, and that is currently coasting out of the solar system at 61,000 kilometers per hour, with no way to ever turn around. The distance has not just slowed the conversation, it has made rescue, in any ordinary sense, completely impossible. If Voyager 1 dies tonight, it dies alone, and no one will even know for a day. It is worth pausing on just how fragile that thread of contact really is, because distance attacks not only the speed of a message, but its very strength. A radio signal does not only take time to cross space, it also spreads out as it travels, thinning and weakening with every kilometre, until by the time it arrives it is almost nothing at all. Voyager 1 transmits with about 23 watts of power, roughly the same as a dim refrigerator light bulb. By the time that signal has crossed 25 billion kilometres and washed over the Earth, it has spread so impossibly thin that the giant dishes which catch it receive only a tiny fraction of a billionth of a watt. The total energy gathered from all of Voyager's transmissions across nearly 50 years is so small that it would be dwarfed by the faint impact of a single snowflake settling onto the ground. We are, quite literally, reconstructing a portrait of interstellar space from a whisper billions of times fainter than the power of a wristwatch battery. To hear a whisper that faint, you need extraordinary ears, and we have only a few of them. Every command we send to deep space, and every reply we receive, passes through the deep space network, a small set of enormous radio dishes spread across just 3 sites on Earth. One in California, one in Spain, and one in Australia, spaced roughly evenly around the planet, so that as the Earth turns, at least one is always facing the outer solar system. This handful of antennas is the entire bridge between humanity and every distant spacecraft we operate, and it is hopelessly oversubscribed, with far more missions needing its attention than it can serve. Each probe granted only scheduled windows of precious listening time. Worse still, the most distant spacecraft depend on a single dish. Because of the path Voyager 1 now follows, only one antenna on the whole of Earth, the great 70-metre dish in Canberra, Australia is capable of sending commands to it. One dish, on one continent, for the farthest object we have ever made. When that dish went down for upgrades, our ability to speak to Voyager went down with it. The data still trickled home at around 160 bits every second, a rate far slower than 1990s dial-up internet. Homde, so sluggish that sending back a single image can take hours. But our ability to talk back, to command, to correct, hung entirely on one piece of machinery in one place. And this thread will not hold forever, for a reason that has nothing to do with any failure. Voyager 1 adds another 3.5 times the Earth-to-Sun distance to its journey every single year, and as it recedes, its signal grows fainter still, spreading thinner across the widening gulf. Its aging power source weakens year by year as well, so that the 23 watts it once transmitted slowly dwindle. Sometime in the next decade or so, the two will cross. The signal will fade below the faintest whisper. Even our greatest dishes can pull from the noise, or the power will fail, and Voyager will fall silent not because anything broke, but simply because it has gone too far. We will not lose Voyager to a malfunction. We will lose it to distance alone. The machine may still be working perfectly, still coasting, still carrying its message into the dark, and we will simply no longer be able to hear it. Distance will have done what no accident could. It will have quietly ended the conversation, one fading word at a time, until there is nothing left to receive. Now, you might think Voyager is an extreme case, a special victim of 50 years and 16 billion miles. So let us pull all the way back in to the nearest object in the sky, the one that feels close enough to touch. The moon sits about 384,000 kilometers away. In cosmic terms, that is nothing, a stone's throw, the very first step off our doorstep. And yet even here, light is not instant. A radio signal needs about 1 1/3 seconds to cross from Earth to the moon, which means a round trip a question, and its answer takes roughly 2.5 seconds. You have heard this delay without realizing it. In the old recordings of the Apollo missions, listen closely to the rhythm between mission control and the astronauts. A controller speaks, and there is a small, strange pause, a beat too long before the reply comes. That pause is not hesitation. That pause is the speed of light, made audible as the words climb all the way to the moon and fall all the way back. 2.5 seconds sounds harmless. But distance does not only steal the reply, It also steals the rescue, and the moon taught us that lesson in the most frightening way possible. In 1970, 3 astronauts were most of the way to the moon aboard Apollo 13 when an oxygen tank exploded in their service module. They were around 330,000 kilometers from home. The radio worked. The famous words, "the calm report of a problem," reached Houston in just over a second. So communication was not the barrier this time. The barrier was everything else. There was no rescue ship. There could be no rescue ship. No vessel on Earth could be fueled, launched, and sent across that gulf in time to reach them. The only people who could save those 3 astronauts were the 3 astronauts themselves, guided by engineers who could talk to them but could never reach them. They survived by turning their lunar lander into a lifeboat, by rationing power and water and breathable air, by flying a crippled spacecraft around the moon and back through a needle-thin corridor in the sky. They lived, but they lived because they rescued themselves. Distance had already decided that no one else could. Hold those 2 ideas together, because together they define this first, smallest reach of the cosmos. Near the Earth, the reply is still fast, but the rescue is already gone. Push only a little farther, and the reply starts to vanish too. Travel out to Mars, our next nearest neighbour among the planets, and the gentle 2-second lag of the moon swells into something that reshapes how missions must be run. Mars and Earth are constantly moving, sometimes on the same side of the sun, sometimes on opposite sides. When the 2 worlds are closest, a one-way signal takes around 3 minutes. When they are far apart, it stretches past 20 minutes. That means a round-trip conversation with Mars can take anywhere from roughly 6 minutes to nearly 3/4 of an hour. This single fact controls the design of everything we send there. When a rover like Curiosity or Perseverance rolls across the Martian surface and approaches the edge of a crater or a field of sharp rock, no driver on Earth is steering in real time. They cannot be. By the time a human in California saw the danger and shouted stop, the warning would arrive 10 or 20 minutes too late, and the rover would already be at the bottom of the ravine. So we do not drive these machines directly. We give them a destination and a measure of intelligence, and we let them inch forward on their own, feeling out the terrain, stopping when something looks wrong, because their human partners are minutes in the past and can never catch up. The rover must be its own driver, its own first responder, its own emergency room. There is no other choice. Picture the precise moment it matters. A rover creeps toward the lip of a slope on Mars, its cameras catching a patch of loose, treacherous soil ahead. On Earth, an operator sees the same image but sees it 20 minutes after the wheels are already there. If that operator shouts a warning, the words will not land for another 20 minutes, long after the rover has either stopped itself or tumbled. So the machine must judge the danger in that instant, entirely alone, because the nearest human capable of helping is, in effect, 20 minutes in the past. Now imagine a human being standing on Mars instead of a robot. Imagine a crew member with a torn suit or a sudden chest pain. There is no calling home for instant help. A frantic radio cry for a doctor goes out, climbs across tens of millions of kilometers, and the answer, even if a doctor is sitting ready at the microphone on Earth, cannot return for up to 40 minutes. In an emergency measured in seconds, a 40-minute round trip is not a delay, it is a wall. The crew on Mars would have to be everything to themselves, because the entire planet of Earth, with all its hospitals and experts and machines, would be permanently a half hour out of reach. We have spent our whole history on a world where help can always, in principle, arrive. Mars quietly erases that promise. It is not only emergencies that distance corrodes. It is the ordinary human comfort of simply talking to home. A crew on Mars, tens of millions of kilometers away, could never hold a live conversation with anyone on Earth. Not with mission control, not with their own families. With a round-trip delay stretching from 6 minutes to 40, every exchange would collapse into something halting and strange. You would speak, then wait through long minutes of silence, then finally hear a reply to something you said half an hour ago, by which point your own thoughts had moved on. There could be no laughter shared in real time, no quick reassurance, no back and forth of an actual dialogue. A call home would feel less like a conversation and more like trading slow letters spoken aloud, each one arriving into a moment its sender could not see. For astronauts who have always known the instant connection of a phone call, This is a profound and deliberate isolation. Every crew that ventures to Mars will have to accept that the warm, immediate voice of home is gone, replaced by a delayed echo, and that for the duration of their mission they are, emotionally as much as physically, on their own. We have sent people to the moon and kept them in near instant contact, a beat of delay and no more. But the moon is the last place where that intimacy survives. Step any farther out, and distance begins to fray even the simplest thread of human conversation, stretching the voices of those we love until they arrive too late to answer the moment that prompted them. The cost of crossing space, it turns out, is paid not only in fuel and years, but in the slow severing of the most basic connection of all, the ability to speak and to be heard right now. And there are moments when Mars does not merely delay our help, but cuts it off entirely. Every 26 months or so, in the slow dance of the two planets around the Sun, Mars passes around the far side of our star, so that the line between Earth and Mars runs directly through the Sun itself. This event is called solar conjunction, and when it happens, the Sun's roaring output of charged particles and radio noise floods the channel between the worlds, corrupting any signal that tries to pass through. A command sent during this time could arrive at Mars scrambled, an instruction transformed into something dangerous or meaningless. So we do not risk it. For around 2 weeks, every time this alignment occurs, mission controllers stop sending commands to their spacecraft on and around Mars altogether. They go silent, on purpose. Think about what that means for anyone or anything out there. For 2 weeks, the rovers and orbiters at Mars are entirely on their own, cut off from Earth not by a delay they can wait out, but by a wall of solar interference that nothing can cross. They are preloaded with instructions to keep themselves safe, to do nothing risky, to simply endure until the planets move and the channel clears. There is no emergency override. There is no breaking through. If something went wrong during those weeks, Earth would not even be able to send a word until the Sun stepped out of the way. This is a new and harsher thing than simple delay. A delayed message still arrives. You only have to wait. But during conjunction, the connection is not slow, it is severed. Distance has conspired with the geometry of our own solar system to raise a temporary but total blackout. A reminder that the link we depend upon is not guaranteed at all and can be erased entirely by nothing more than where the planets happen to stand. And every barrier we have seen so far, remember, lies within a region light can cross in mere hours. The true gulfs have not even begun. And Mars is still close. Keep going. At Jupiter, more than 5 times farther from the Sun than the Earth, a one-way signal takes somewhere between about 35 and 52 minutes, depending on where the two worlds sit in their orbits. A simple round-trip exchange with a spacecraft at Jupiter can eat up an hour and a half. The Galileo and Juno probes that have studied Jupiter could never be flown like aircraft with a pilot reacting moment to moment. They had to carry their own judgment, their own preloaded plans, because their controllers were always more than half an hour behind reality. Out at Saturn, the lag grows past an hour each way. The Cassini spacecraft, which spent 13 years circling that ringed world, executed many of its most delicate maneuvers entirely on its own, following instructions written and sent days in advance, because by the time Earth could have reacted to anything, the moment would have long since passed. Then comes the realm that truly humbles us, the outer solar system, where the numbers stop sounding like communication delays and start sounding like the answer to a different question entirely. Light from the Sun reaches the Earth in about 8 minutes. We are bathed in sunlight that left its source before we ever saw it. By the time light crawls all the way out to Neptune, the most distant true planet, it has been travelling for around 4 hours. And at Pluto, that small frozen world on the threshold of the outer dark, sunlight arrives only after roughly 5 hours of travel. When the New Horizons spacecraft swept past Pluto in the summer of 2015, the radio signals carrying its first close photographs needed about 4.5 hours to reach the Earth. Mission controllers sat in a room and waited through an afternoon, knowing that the spacecraft had already either succeeded or failed hours earlier, that the entire encounter was finished and frozen in the past, and that all they could do was wait for the news of something that had already happened to finish arriving. That waiting reveals a distinction we have to make carefully, because the whole rest of this story depends on it. There is the time it takes for light, or a radio message to cross a distance. And there is the time it takes for a physical spacecraft, made of metal and carrying fuel, to cross that same distance. These two numbers are not even close to one another, and the gap between them is one of the cruelest facts in all of space travel. Look again at New Horizons. Its radio signal from Pluto took about 4.5 hours, but the spacecraft itself, one of the fastest objects we have ever launched, needed 9.5 years to make that same journey. Light did it in an afternoon. The machine did it in nearly a decade. Light delay is measured in hours at the edge of the planets. Physical travel to that same edge is measured in years. When people casually say that something is 5 light hours away, it is easy to hear that as if it were a short trip. It is not a trip at all in human terms. It is a signal time. The actual voyage, for anything we can build, is a journey that consumes a sizable fraction of a career. And the planets are not the edge of anything. They are barely the beginning. Beyond Pluto, the sun's influence keeps reaching outward in the form of the solar wind, a thin gale of particles streaming away from our star in every direction. That wind carves out a vast bubble around the entire solar system called the heliosphere, and only when you pass beyond its outer boundary, the heliopause, are you truly in interstellar space. Voyager 1 crossed that boundary in August of 2012, after 35 years of flight, at a distance of about 120 astronomical units from the Sun, 120 times farther from the Sun than the Earth is. It had been travelling for over 3 decades just to leave the bubble. But even the heliopause is not the real edge of the Sun's domain. Far, far beyond it lies the Oort cloud, a colossal spherical shell of icy bodies that surrounds the entire solar system like the faint rind of a fruit. Its inner boundary may begin around 2,000 astronomical units out. Its outer reaches may extend to 100,000 astronomical units or more, stretching nearly halfway to the next star. This is still the Sun's territory. These distant icy worlds still feel its gravity, still loosely orbit it, still belong to our solar system. And Voyager 1, our fastest, farthest ambassador, racing outward at 61,000 kilometers per hour, will not even reach the inner edge of the Oort cloud for about 300 more years. To pass all the way through it, out the far side and into the open gulf beyond, would take that spacecraft something like 30,000 years. Sit with that for a moment, not as poetry but as plain engineering. A machine that has already flown for nearly 50 years, that is already the most distant object we have ever made, that crosses billions of kilometers every year, would need 300 more years just to arrive at the inner shell of our own solar system's outermost layer, and 300 centuries to leave it behind. The reach of the system we call home is so enormous that our greatest journey so far has not finished crossing it, and will not finish in any time span that means anything to a human life. This is the territory where these consequences stack one upon another. Distance broke the conversation first, back at the moon, where the reply began arriving a beat too late. It broke the rescue almost as quickly, on Apollo 13, where help could never physically come. It deepened at Mars, where minutes of delay forced our machines to think for themselves and would leave a stranded astronaut beyond the reach of any real-time help. It widened at Jupiter and Saturn, where every important decision had to be made in advance, blind to whatever the spacecraft was actually facing. And it became almost incomprehensible at the outer edge, where the difference between a signal and a ship grew from hours into years, and where the Sun's own backyard turned out to be so vast that we have not crossed it in half a century of trying. And notice what every one of these problems has in common. None of them is about danger in the ordinary sense. What undid us in every case was nothing more dramatic than the gap itself, the sheer number of empty kilometers lying between us and whatever we were trying to reach. Voyager 1 is not broken by radiation or sabotage. It is isolated by 23.5 hours of one-way light time. The Mars astronaut is not killed by an alien. They are stranded by 40 minutes of round-trip delay. At every scale we have examined, nothing reached out to harm us at all. Distance withheld the reply, withheld the rescue, withheld the chance to react in time. And it has done all of this without us ever leaving the Sun's own gravitational neighborhood. Here is the part that should genuinely unsettle you, though. The part that turns this from a story about engineering into a story about everything that comes next. For all its staggering size, for all the centuries it would take to cross, the entire solar system, the planets, the heliosphere, the Oort cloud, the whole enormous bubble of the sun's influence is, on the scale of the cosmos, very nearly a single point. Light needs only about a day to reach Voyager 1. It would need only around a year and a half to reach the far edge of the Oort cloud. That is the full width of our home, measured in light. Hours to the planets, a day or two to our farthest machine, perhaps 18 months to the outermost icy shell, and the very next thing out there, the closest other star to our sun, is more than 4 light-years away. Stop and feel the size of that jump. We just spent all of this watching distance dismantle our ability to talk and to help, and we did it all within a region light can cross in a day or two. The gap to the nearest star is not a little bigger than that. It is thousands of times bigger. Everything we have struggled with so far, the day-long delays, the impossible rescues, the decades of travel happened inside a space that is itself a rounding error, next to the emptiness that begins where the solar system ends. Voyager 1 has flown for almost 50 years. And if you measured how far it has travelled against the distance to that nearest neighbouring star, it would have completed roughly 0.03% of the trip. Not 3%, 0.03%. After half a century, at 61,000 kilometers per hour, our farthest spacecraft has barely stepped off the porch. So distance, at this first scale, has already taken the reply and the rescue, but it has done so while still letting us hold on to one final comfort, one assumption we have not yet been forced to surrender. Inside the solar system, no matter how long the delay, a mission can still be measured in human terms. A career, a working life. Engineers who launched a probe can still be alive to see it arrive. The people who said goodbye to New Horizons watched it reach Pluto less than a decade later. The men and women who built Voyager have followed it for 50 years. The delays are brutal, but the journeys still fit, just barely, inside a single human span. That is the assumption about to be destroyed, because the moment we leave this bubble and aim for that nearest star, distance stops merely delaying our messages and starts outliving the messengers themselves. The next gap is not measured against an afternoon, or a career, or even a long human life. It is measured against generations. And to understand why the void between the stars is a fundamentally different kind of barrier than anything we have just seen, why crossing it would outlast not just a mission but everyone who ever worked on it, we have to step off the porch entirely, into the dark between the sun and its neighbours. Step off the edge of the solar system, out past the last icy bodies of the Oort cloud, and point yourself toward the nearest star. You are now facing Proxima Centauri, a small, dim red dwarf that sits about 4.2 light-years away. It is the closest other sun to our own, the very next island of light in the dark, and reaching it is the shortest interstellar journey that physically exists. There is nothing nearer. And yet this shortest of all star crossings is about to take everything that broke a moment ago. The delayed reply, the impossible rescue, the years of travel, and stretch it past the breaking point of a human life itself. To understand why, we first have to be honest about what a light year actually is, because the phrase fools almost everyone who hears it. A light year sounds like a measurement of time. It is not. A light year is a distance. It is the distance that light, moving at 300,000 kilometers every second, travels in one full year. Work that out and a single light year comes to roughly 9.5 trillion kilometers, about 6 trillion miles. So when we say Proxima Centauri is 4.2 light years away, we are not saying it takes 4 years to get there. We are saying that even light, the fastest thing the universe permits, needs 4.2 years just to cross the gap. Anything slower, which means anything we have ever built or could plausibly build, needs vastly, almost unbelievably, longer. How much longer? Take the emptiness itself first, because the distance between stars is not merely large, it is a kind of vacuum so complete that our instincts have no grip on it. Imagine shrinking the sun down until it was the size of a basketball sitting on a court in one city. On that same scale, the Earth would be a grain of sand about 30 meters away, and the entire solar system out to Neptune would fit inside a modest neighbourhood. Now, Where would the nearest star be, that next basketball? It would not be in the next town. It would not be in the next country. On that scale, the nearest other basketball would sit roughly 6,000 kilometers away in another city on another continent entirely. Between those two basketballs, there would be almost nothing. No stars, no planets, no warmth, just a vast cold gulf of empty space so wide that the two suns might as well be unaware the other exists. That is the true texture of our galaxy, not a crowded sky full of neighbours, but tiny, lonely points of fire separated by oceans of nothing. Now put a real spacecraft into that gulf and watch what happens to time. Voyager 1, the machine we followed a little earlier, is travelling at about 61,000 kilometers per hour. That is faster than any bullet, faster than anything most people will ever picture moving. Voyager is not aimed at Proxima Centauri, but if it were, if you could turn it and send it straight toward the nearest star, it would arrive in roughly 73,000 years. Not 73, 73,000. To put a human shape on that number, the entire span of recorded history, from the first written word to this sentence, is only about 5,000 years. Our fastest interstellar probe would need that whole span of history to pass more than 14 times over, just to reach the closest star to our own. And Voyager will never even do that, because it is not headed toward any star in particular. It is simply falling outward through the galaxy, and the cold mathematics of its path means that in about 40,000 years, it will drift within 1.6 light-years of a faint red dwarf called Gliese, 445, and even that is not an arrival, but a distant passing, a ship sliding by a lighthouse it will never visit. This is the fate of our greatest voyagers. They do not reach other stars. They wander between them forever, growing colder and quieter, and the stars take no notice. And yet we sent something with them anyway, knowing all of this. Bolted to the side of each Voyager spacecraft is a gold-plated disc, a phonograph record sealed in a protective case, built to survive for 1 billion years or more in the vacuum of space. On it, a small team led by the astronomer Carl Sagan encoded a portrait of our entire world, greetings spoken in 55 languages, the laughter of a child, the sound of rain and surf, and a human heartbeat, music from across the earth, and more than 100 images of who and what we are. Etched into the cover are instructions, written in the universal language of physics, explaining how to play it and how to find the world it came from. Think carefully about what this object is, because it is the purest expression of everything we have been circling. The golden record is a message with no expectation of a reply, not a delayed reply, not a reply across generations, but no reply at all, ever by design. Its makers knew the spacecraft would not reach any star for tens of thousands of years, and would not come near one for 40,000. They knew that whatever might one day find it, if anything ever does, would be separated from us not by years or centuries, but very likely by spans longer than our species has existed. They were not writing to anyone alive. They were not writing to anyone's children, or their children's children. They were writing to the deep future itself, casting a letter into a distance so great that the very concept of an answer dissolves. This is what distance does to communication once it stretches between the stars. It does not merely slow a conversation, it removes the other half of the conversation entirely. The golden record is humanity speaking into a silence so vast that we have already accepted. We will never hear anything back, a letter addressed to no one in particular, postmarked to a moment so far away that everyone who wrote it, and everyone who will ever read these words, will be long gone before it could possibly be opened. We did not send it expecting contact. We sent it because the alternative was to send nothing at all, and to vanish without ever having spoken. Against a distance that outlasts every human life, a message built to outlast the human species was the only kind of message that made sense. You might hope that we could simply build something faster. And we have built faster. The Parker Solar Probe, whipping around the Sun on the energy of our star's own gravity, briefly reached close to 700,000 kilometers per hour, making it the fastest object human hands have ever made. But that is a momentary peak, achieved by falling sunward, not a cruising speed you could carry to another star. Even if you somehow could hold that blistering pace the entire way, a trip to Proxima Centauri would still take more than 6,000 years. 6,000 years at the fastest speed we have ever achieved by any machine under any conditions. The barrier is not that our rockets are a little too slow. The barrier is that the distance is so enormous that even our absolute best falls short by factors that swallow entire civilizations whole. This is the new thing that distance does at this scale, the consequence that did not exist before. Inside the solar system, the delays were brutal, but a mission still fit inside a human life. The people who built Voyager have followed it for 50 years, and many are alive today. The team that waved goodbye to New Horizons watched it reach Pluto less than a decade later. The journeys were long, but the travelers and the watchers were the same people. Cross into interstellar space and that quietly ends. A ship sent to even the nearest star at any speed we can actually reach would outlive every single person who launched it. The engineer who designs the engine, the technician who tightens the final bolt, the family that watches the launch, all of them would be dust, and their grandchildren's grandchildren's grandchildren would be dust before the ship arrived. Distance has stopped delaying the message. It has begun outliving the messenger. And here is where something remarkable enters the story, because nature has already shown us, with its own hand, exactly how isolated these stellar islands are. In July of 2025, astronomers spotted a faint object moving through the inner solar system on a path that made no sense for anything born here. Its orbit was not a closed loop around the sun, but an open, hyperbolic trajectory, and its speed was far too high to be one of our own. It was named 3I Atlas, the third interstellar object ever confirmed, a visitor from around another star entirely. By June of 2026, careful study had settled what it was. Not a spacecraft, not anything artificial, despite the inevitable speculation, but a natural comet, an ancient ball of ice and dust, possibly older than the Sun itself, flung out of some distant planetary system long ago and drifting between the stars ever since. Think about what 3I Atlas represents. Here was a piece of another solar system, and it reached us. So material can cross the gulf between stars. But look at how it crossed. It tore through our solar system at around 60 kilometers per second, roughly twice as fast as our fastest rockets, and even at that tremendous speed, the journey from its home star to ours took not centuries, not millennia, but almost certainly hundreds of millions, perhaps billions of years. It was not steered, it was not crewed, it was simply thrown into the dark and left to fall for a span of time longer than the existence of complex life on Earth, until pure chance happened to carry it past our sun. And now it is leaving again, sliding back out toward Jupiter and beyond, never to return, vanishing into the same emptiness it came from. Nature can move things between the stars, but it does so on timescales that make a human lifetime look like the blink of a single afternoon. That is the deep meaning of interstellar distance, and it is why planetary systems are not neighbours in any sense we would recognise. Each star with its family of worlds is a sealed island, separated from every other island by gulfs that take light years and physical travellers tens of thousands of years to cross. Our Sun and its planets are one such island. The Alpha Centauri system, where Proxima Centauri keeps its lonely orbit around the two brighter stars Alpha Centauri A and Alpha Centauri B, is the nearest other island. And we have already found that Proxima Centauri holds at least one planet, a world called Proxima B, confirmed in 2016, orbiting in the zone where liquid water could in principle exist. So there is a planet around the nearest star. There may even be somewhere worth going. And it is still, for all practical purposes, unreachable across the span of any life that could decide to make the trip. If a single human life cannot survive the journey, perhaps many lives can be chained together to outlast it. This is the idea behind a generation ship, and it is one of the few honest answers to interstellar distance that does not require breaking the laws of physics. The concept is simple to say and staggering to absorb. You build a vessel large enough to be a closed, self-sustaining world, air, water, food, soil, everything recycled across centuries. You crew it with people who understand a hard truth. They will live their entire lives aboard, raise children aboard, grow old and die aboard, and never see the destination. Their grandchildren, or their great-great-grandchildren, born in transit, knowing no other home, would be the ones to finally arrive at a star their ancestors only dreamed of. The travelers who finished the voyage would be different people from the ones who began it, separated from the launch not by distance but by the slow accumulation of generations. This is not a delay you wait out. It is a delay you must hand down, like an inheritance, to people who do not yet exist and never agreed to carry it. Every assumption we have about a journey that you set out, you travel, you arrive dissolves. On a generation ship, one group sets out, and a completely different group, their descendants, arrives. The distance is so great that it has to be crossed not by a person but by a lineage, and the success of the mission depends on a society holding itself together in a sealed metal world for longer than most human empires have ever lasted. Of course, people will reach for the shortcuts, and it is worth being honest about them, because they are real ideas pursued by serious people, but they remain firmly in the realm of the speculative, not the built. The most ambitious is a concept called Breakthrough Starshot, proposed in 2016. The idea is to abandon heavy crewed ships entirely, and instead launch a swarm of tiny featherweight probes, each one a chip with a thin reflective sail, and then push them with an enormous bank of ground-based lasers. In principle, such a sail could be accelerated to around 20% of the speed of light. At that pace, a probe could cross to Alpha Centauri in roughly 20 years within a human lifetime at last. It is a beautiful idea, but it exists only on paper and in laboratories. No such laser array has been built, no sail has survived such forces, and even if it all worked perfectly, the probes would be gram-sized cameras, not colonists. They would flash past Proxima Centauri in a matter of hours, snapping a few images, with no way to slow down, and then sail onward into the dark forever. We would get a postcard, not a foothold. But suppose we set aside the featherweight probes and ask the harder question, what happens to a human crew that somehow does reach a large fraction of the speed of light? Here the universe offers something genuinely strange, a loophole that feels almost like mercy until you see its price. Einstein's relativity tells us that time itself is not the same for a fast-moving traveller as it is for those left behind. The closer you push toward the speed of light, the more slowly your own clock runs compared to the clocks of the world you left. At 99% of light speed, time aboard the ship would crawl so slowly that the crew might age only a single year while 7 years passed on Earth. Push closer still, and the gap widens without limit. On its face, this seems to break the wall we just built. If the crew's own time slows down, then perhaps a crossing that takes decades or centuries as measured from Earth could be lived through in just a few years by the people aboard. A traveller moving fast enough could, in principle, cross not just to Proxima Centauri but deep into the galaxy within their own lifetime, their personal clock idling while the cosmos outside races ahead. The journey would fit inside a life after all, but only inside the traveller's life, and only by sacrificing everything outside it. Because here is the cruelty hidden inside the loophole. The slowing of the traveller's clock does nothing to slow the clock back home. While the crew experiences a few short years, the Earth they left behind experiences the full, brutal span of the journey, decades, centuries, however long it truly takes. A traveller who reached a distant star and turned back, aging only a handful of years in the process, would return not to the world they knew, but to one that had aged hundreds or thousands of years in their absence. Everyone they ever loved would be long dead. Their language might be forgotten. Their nation might have risen and fallen and been replaced many times over. The traveller survives the distance, but only by being severed from their own time completely, arriving home as a living relic from a vanished age, a stranger to the very civilization that sent them. So even relativity, which seems at first to hand us a way through, only relocates the loss. It does not let a traveller beat the distance. It lets a traveller outlive themselves, at the cost of outliving everyone and everything they ever knew. Distance, at this scale, does not merely outlast a single human life. It forces an impossible trade. You may keep your own years, or you may keep your world, but the gulf between the stars will not let you keep both. And all of this assumes you could reach such speeds in the first place, which conceals perhaps the hardest physical wall of all. Going fast is not free. To accelerate a spacecraft to a large fraction of the speed of light, you must pour in a quantity of energy that climbs to almost unimaginable heights, and the faster you wish to go, the more violently that cost escalates. The energy needed does not rise gently with speed. It surges upward, demanding more and more for each additional increment, until approaching the speed of light would require energies beyond anything we can presently produce or even sensibly describe. Consider just a modest crude ship pushed to even a tenth or a fifth of light speed. The kinetic energy locked into that moving vessel would rival a meaningful fraction of all the energy human civilization generates in years of effort, and that is only to get the ship up to speed. Then comes the part everyone forgets. A ship that accelerates must also decelerate, or it will simply tear past its destination in a blur and continue into the dark forever, exactly as our real probes do. To actually arrive somewhere, to slow down and stop at the target star, you must spend that staggering energy budget all over again. In reverse, the true cost is not one fortune in energy, it is two, one to leave and one to arrive. Watch what this does even to our successes. When New Horizons reached Pluto, it did not arrive in any settled sense. It flashed past at nearly 50,000 kilometers per hour, with no fuel to slow down, gathering what images it could in a few frantic hours before hurtling onward into the dark forever. The interstellar comet 3I Atlas did the same to us, tearing through and gone. This is the rule, not the exception. Without the colossal energy to brake, every traveller is condemned to glimpse its destination in passing and never stay. Where would such energy come from? Chemical rockets, the kind that lift our spacecraft today, are hopelessly inadequate. They could never carry enough fuel, because the fuel itself has weight that must also be accelerated, a spiral that defeats itself. Even the most advanced concepts physicists have sketched engines driven by nuclear fusion or by the annihilation of matter and antimatter. The most concentrated energy release known to science strain against limits that make a fast interstellar crossing extraordinarily difficult. And the more exotic shortcuts that fill our imaginations, warp drives and the folding of space, require ingredients that have never been shown to exist in nature, forms of energy with properties we have never observed and may never find. So the wall between the stars is not a single barrier but three, standing one behind another. There is the distance itself, which outlasts any life. There is the relativity that, even conquered, would sever a traveller from their own world. And there is the raw energy, a price so steep that simply reaching the speeds that would make any of it possible lies beyond our power. Each of these alone would be enough to seal the stars away. Together, they explain why, after all our dreaming, the nearest sun remains a place we can see, study, and long for, but not, in any lifetime we can presently imagine, a place we can go. And notice that even the dream of speed does not dissolve the deeper problem, because the problem was never only about travel, it was about contact. Suppose, against all odds, we did establish a colony around Proxima Centauri. The moment we did, distance would impose its toll on every word exchanged between the two worlds. A message from that colony to Earth, travelling at the speed of light, would take 4.2 years to arrive. A reply would take another 4.2 years to return. A single round of conversation, a question, and its answer would consume more than 8 years. A child born on Earth the day a question was sent to Proxima could be in school by the time the answer came home. There would be no discussion, no negotiation, no shared moment of decision between the two human worlds. Just messages crossing in the dark, each one already years old when it arrived, each sender long since moved on by the time their words were read. Two branches of humanity, around two neighbouring stars, would be more isolated from one another than any two peoples in the whole of Earth's history. This is the wall that defines the realm between the stars. Within the solar system, distance stole the instant reply and the possibility of rescue, but it left the journey small enough to fit inside a lifetime. Out here, between the stars, it takes that last comfort too. The journey no longer fits inside a life. It does not fit inside a dozen lives. The nearest star demands either a chain of generations or a technology we have only sketched, and even success would leave the two worlds talking past each other across an 8-year gulf of delay. We have not encountered a single hazard along the way, no radiation storm, no hostile world, no failure of any machine. The only adversary, again, is the raw separation between one sun and the next. And that separation has quietly redefined what a journey even is. Yet for all of this, we are still talking about the very closest star. Proxima Centauri is the easy case, the short trip, the next basketball on the next continent. Widen your view just slightly and the picture grows heavier still. Within about 12.5 light years of the Sun, there are only around 30 stars, 30 fires scattered through a sphere so vast that light itself needs over a decade to cross from one side to the other. Barnard's star, Wolf 359, Sirius the Alpha Centauri trio, these are our entire neighbourhood, our local handful of suns, and reaching even the nearest of them is a multi-generational undertaking that no human society has ever come close to attempting. The richest, fullest map of everywhere we could ever realistically hope to send a crewed ship contains only a few dozen destinations, and every single one of them lies beyond the reach of any life now living. And those few dozen stars are themselves nothing. They are a tiny knot, a faint cluster of dots, gathered in one small corner of a far larger structure. Our Sun and all its neighbouring suns sit together inside a minor spiral arm of the Milky Way galaxy, a feature called the Orion Arm. Step back far enough to see the whole galaxy, and our entire local collection of stars, every destination we just called impossibly far, would vanish into a single unremarkable speck, lost among hundreds of billions of other stars wheeling around a distant galactic centre. We have just spent all this time discovering that crossing the gap to the nearest star outlasts every human life, that even nature needs hundreds of millions of years to drift a comet between two suns, that the closest dozens of stars together form a neighbourhood no one alive could ever traverse. And all of it, the Sun, Proxima Centauri, Barnard's star, the entire local swarm fits inside a region the galaxy would not even notice. The Milky Way is about 100,000 light-years across. Our whole interstellar neighbourhood spans barely a dozen. To go from one side of our local cluster of stars to the other is a journey beyond lifetimes. To go from one side of the galaxy to the other is a journey of a different order entirely, one measured not against a life, not against a chain of generations, but against the rise and fall of whole civilizations. Because at the scale of the stars, distance learns to outlast the people who travel. At the scale of the galaxy, it learns to outlast the people who remember why anyone left at all. And to see how a gulf can swallow not just a lifetime, but the entire memory of a civilization, we have to leave our small arm of suns behind and confront the size of the galaxy itself. Lift yourself out of the Orion Arm and rise high above the flat disk of the Milky Way until the whole thing wheels beneath you like a slow, luminous storm. From here, our entire interstellar neighbourhood, Proxima Centauri, Barnard's star, the whole local swarm of suns that defeated lifetimes and generations a moment ago collapses into a single dim point, indistinguishable from the haze of stars around it. What spreads out below you instead is a vast rotating wheel of light, perhaps 100,000 light-years from edge to edge, holding somewhere between 100 and 400 billion stars. This is the structure that contains everything we have discussed so far, and it is so large that crossing it does not merely outlast a traveller or a bloodline. It outlasts the very idea of a continuous civilization remembering why the journey began. Begin with the number that does the damage, 100,000 light-years. We establish the meaning of a light-year carefully before a distance. The span light covers in a year, around 9.5 trillion kilometres. So the width of our galaxy is 100,000 of those spans laid end to end. Light itself, the fastest thing permitted to exist, needs 100,000 years to cross from one rim of the Milky Way to the other. Take a moment to anchor that against ourselves. 100,000 years ago, our species already existed, but lived only in small scattered bands, with no writing, no agriculture, no city, no nation, no recorded thought of any kind. A beam of light that set out across the galaxy when the first modern humans were stirring in Africa would only now, today, be arriving at the galaxy's far side. The galaxy is so wide that a single one-way crossing at the speed of light spans the entire existence of humanity as a distinct kind of creature, and that is only light. Recall what physical travel does to these numbers. Voyager 1, at 61,000 kilometers per hour, would need around 73,000 years just to reach the nearest star, 4 light-years away. Scale that same crawl up to the full width of the galaxy, and the figure becomes almost meaningless well over 1 billion years of flight to cross the Milky Way at the speed of our fastest probe. The Earth itself is only about 4.5 billion years old. A ship leaving one edge of the galaxy at Voyager's pace, bound for the other, would consume more than 1/3 of our planet's current age on the journey. There is no human frame, no civilizational frame, perhaps no biological frame at all that can hold a span like that. The galaxy is not a place you cross, it is a place you are born inside, live inside, and die inside, having moved across an utterly trivial fraction of it. Even the galaxy's own turning runs on this scale. The Milky Way rotates, slowly, majestically, and our sun rides that rotation as it circles the galactic center. One full orbit, one lap of our solar system around the heart of the galaxy takes roughly 230 million years. The last time the sun was in its current position on that great circular track, dinosaurs had not yet risen to dominate the Earth. A single galactic year swallows the entire age of mammals, the rise and fall of countless species, the drift of continents across the face of the planet. We are not passengers on a quick carousel. We are riding a wheel so vast that one turn outlasts entire chapters of life's history on Earth, and we have completed only about 20 such turns in the whole lifetime of the Sun. And at the still point around which that whole vast wheel turns, at the very centre of the galaxy, sits something we can never visit and can barely even glimpse. It is a black hole of monstrous scale, Sagittarius I star, a concentration of mass equal to roughly 4 million suns crushed into a single point, sitting at the very centre of the galaxy. Every star in the Milky Way, our own included, wheels around this dark heart. It is, in the most literal sense, the centre of our world, and it lies about 26,000 light-years away from us, buried deep in the crowded, dust-choked core of the galaxy. Consider how strange our relationship with this object is. It is the anchor of everything, the centre about which 100 billion stars sweep, the place our sun has been faithfully orbiting for the entire history of the Earth. You might expect such a thing to blaze in our night sky, an obvious landmark at the heart of the heavens. Instead, we cannot see it at all with ordinary eyes. Between us and the galactic centre lie 26,000 light-years of stars, gas, and thick clouds of dust that swallow visible light almost completely, hiding the core behind an impenetrable veil. For most of human history, we did not even know it was there. Only by gathering radio waves and infrared light, which pierce the dust where ordinary light cannot, did we finally confirm the black hole's existence. And only in 2022 did astronomers manage to capture an actual image of it, a faint ring of glowing matter encircling the darkness, assembled from observations gathered by telescopes spread across the entire planet. So here is the centre of our galaxy, the central point every star in the Milky Way circles, the throne at the core of our entire stellar empire, and it is both unreachable and nearly invisible. 26,000 light-years means that even at the speed of light, a signal would need 26,000 years simply to reach the heart of our own galaxy, and far longer than the age of human civilization to send anything physical even that far. We orbit a centre we can never approach, anchored to a landmark we cannot even properly see. If distance can hide the very hub of our own galaxy from us, keeping us forever circling a place we will never visit, then the prospects for crossing the galaxy's full breadth begin to look bleaker still. This is where distance reveals an even crueler face, the consequence that did not exist at the smaller scales. Within the solar system, distance broke the instant reply. Between the stars, it broke the human lifespan, demanding generations to cross a single gap. Across the galaxy, it breaks something larger and more fragile than any individual life. It breaks the continuity of a civilization. It breaks the ability of a people to send something out and still be there, still be the same culture, still remember the question, when the answer finally returns. To feel why, imagine the most patient interstellar empire you can. Suppose a civilization somewhere in the Milky Way decided to send a message clear across the galaxy, and suppose another civilization on the far side decided to answer. The message crawls outward at the speed of light for 100,000 years. The reply crawls back for another 100,000 years. A single exchange, one statement and one response consumes 200,000 years. No civilization in the history of the Earth has lasted even a 50th of that. The oldest continuous human cultures are measured in mere thousands of years. Whole languages are born, flower, and die in far less time. Empires that once seemed eternal vanish in centuries. Ask yourself what would still be standing, still speaking the same tongue, still caring about the same question, after 200,000 years of waiting. The honest answer is almost certainly nothing. The civilization that sent the message would be long gone, transformed beyond recognition, or simply extinct before its own answer came home. The galaxy is so large that it does not merely delay a conversation. It guarantees that no single conversation can ever be completed by the same civilization that started it. You can shrink the example and the horror does not lessen. Forget crossing the whole galaxy. Imagine two thriving, star-spanning societies on opposite sides of the galactic center, perhaps 30,000 light-years apart. A greeting takes 30,000 years to arrive, a reply 30,000 more. 60,000 years for a single round of hello. That lone exchange spans more than 5 times the stretch since the last ice age ended long enough for the sender's world to change beyond recognition before the reply arrives. This is not communication in any sense we understand. It is the cosmic equivalent of carving a message into stone, dropping it into an ocean, and hoping that some unimaginably distant descendant of the intended reader might one day find it, with no possibility of ever knowing whether they did. This is the death of the two-way relationship. And it is worth pausing on how total it is. Everything that makes contact meaningful, the back and forth, the clarification, the negotiation, the shared moment of arriving at an understanding together, depends on a reply that comes while you still exist to receive it. At the galactic scale, that is simply impossible. You can broadcast. You can shout into the dark. But you can never have a conversation, because the second half of any exchange arrives in an era so distant that the sender has become history, myth, or dust. A galaxy-spanning civilization, even one that filled every star, could never function as a single coordinated whole. Its distant regions could never govern together, never decide together, never know one another in real time. They would be islands of awareness separated by tens of thousands of years of silence, each one effectively alone, each one talking to the deep past whenever it tried to talk to anyone far away. Here is a way to hold it. Think of the galaxy as a single immense city, so wide that you could photograph the whole of it from a great height, taking in its full sprawling shape in a single glance. You could map it. You could admire it. You could point to a distant district and say, "There, that is where I would like to go." And yet you could never walk across it, never send a runner to the far side and receive word back, never coordinate the near streets with the distant ones, because any messenger you dispatched would die of old age 1,000 times over before reaching the other rim, and any reply would take longer than your nation has existed. You can see the whole city. You can never cross it, and you can certainly never run it. The galaxy grants us the photograph and forbids us the journey. It lets us behold the structure entire while denying us any real passage through it. And we should be precise here, because this is exactly the kind of place where casual language smears two very different ideas together. To see the galaxy is not the same as to reach it, and neither is the same as to converse with anything inside it. We can see across 100,000 light years easily the light arrives on its own, for free, no journey required. We could, in principle, and over impossible spans of time, physically reach distant parts of it, though no traveller or civilization could survive the trip. But we could never hold a living exchange with anything that far away, because the reply outlasts the asker. 3 different barriers: seeing, reaching, conversing, and they fail at 3 completely different thresholds. Seeing fails almost never. Conversing fails first and hardest. Reaching fails somewhere in between. Keep these separated, because as we climb to the largest scales, they will pull apart even further, until we reach things we can see perfectly well, and yet can never touch by any means at all. There is a way to test just how thoroughly the galaxy defeats us, and it comes from imagining the most patient explorer conceivable, Suppose a civilization did not try to cross the galaxy itself, but instead built a single self-replicating probe, a machine that travels to a nearby star, mines raw materials there, builds copies of itself, and sends those copies onward to the next stars, which build more copies still. Each generation of probes fans outward, doubling and doubling, spreading like seeds on the wind. Even at modest speeds, far below that of light, such a wave of self-building machines could, in principle, touch every star in the Milky Way in only a few million years. On the scale of the galaxy's age, a few million years is almost nothing a single afternoon in the life of the cosmos. This is a startling result, and people often raise it as a sign of hope, a way that a civilization might explore the whole galaxy without any single traveler crossing it. But look closely at what it actually delivers, because it confirms the very thing we have been building toward. The probes might reach every star, but the civilization that sent them could never coordinate with them, never receive their reports in any timely way, never act on what they found. A probe at the galaxy's far rim would send its discoveries home across 100,000 years of light travel time, arriving in an era so distant that the senders would almost certainly no longer exist. The wave of exploration would outrun the civilization that launched it, spreading across the galaxy while its makers rose, flourished, and vanished. The reports trickling back into an empty mailbox. Exploration, perhaps. Contact, never. The galaxy permits the spread of machines across galactic time. It forbids the spread of a living, coordinated society. This same brutal arithmetic may quietly answer one of the oldest questions we ask when we look up. If the galaxy holds hundreds of billions of stars, and surely many worlds, where is everyone? Why does the sky seem so silent? There are many possible reasons, but distance alone is enough to explain a great deal of the silence without invoking anything else. Imagine the galaxy were full of civilizations, thousands of them, scattered across its 100,000 light-year breadth. Even then, any two of them would be separated, on average, by thousands or tens of thousands of light-years. A signal between them would take millennia to cross. A reply would take millennia more. Two civilizations might both be broadcasting, both be listening, both be desperate for company, and still never complete a single exchange, because each would be long gone, or transformed beyond recognition before the other's reply arrived. The galaxy could be teeming with voices and still feel empty, not because no one is speaking, but because the distances are so vast that no two speakers can ever hold a conversation within the lifetime of either. The silence of the galaxy, in other words, may not be the silence of an empty room. It may be the silence of a hall so enormous that every voice fades to nothing long before it can cross to another ear. And that is perhaps the loneliest thing distance has done yet to make even a crowded galaxy feel like a void, simply by spreading its inhabitants too far apart to ever truly meet. For now, though, even the galaxy is not the end of the climb. The Milky Way, for all its 100,000 light-year breadth, for all the billions of stars it cradles, is itself only one member of a small cluster of galaxies bound together by gravity. We call this cluster the local group, and it contains more than 50 galaxies, most of them small dim dwarf galaxies orbiting the two genuine giants. One of those giants is our own Milky Way, the other is a great spiral named Andromeda, and Andromeda is about to teach us that the gaps between galaxies are a different order of emptiness than anything we have met before. Andromeda lies roughly 2.5 million light-years away. The width of our entire galaxy was 100,000 light-years. The distance to the next major galaxy is 2.5 million 25 times the full span of the Milky Way, laid out as empty space between us and them. And it is empty in a way the inside of a galaxy is not. Within a galaxy, however vast the gaps between stars, there are still stars, still gas, still the warm machinery of a living disk. Between the galaxies stretches a void so profound that you could travel for 1 million light-years and pass almost nothing at all. No stars, no worlds, just thin wisps of gas and the cold dark and the faint pull of distant gravity. If the gulf between two stars was a barrier no ship could ever cross, the gulf between two galaxies is an emptiness so much greater that the galaxies themselves, those wheels of 100 billion suns, become the lonely specks, separated by distances that dwarf their own enormous bodies. Now look up at Andromeda on a dark autumn night. and you genuinely can, with your own eyes, a faint smudge of light in the constellation that bears its name. The light landing on your eye left Andromeda about 2.5 million years ago. It began its journey when our genus was only just emerging, when our ancestors had barely begun chipping crude tools from stone, when creatures not quite human still walked the African savanna. That light has been crossing the void between two galaxies for the entire span of human becoming, and only now, tonight, does it complete its trip and touch your eye. You are not seeing Andromeda as it is. You are seeing Andromeda as it was, 2.5 million years deep in the past, a portrait so old that the species looking at it did not yet exist when the portrait was painted. This forces a distinction we must now make very carefully, because the rest of this story will live or die on it. When you look at Andromeda, the light you receive has already travelled 2.5 million light-years to reach you. That is the distance the light has crossed its light travel time, the age of the message. But Andromeda is not sitting where that light suggests, frozen, waiting. In the 2.5 million years the light was in transit, Andromeda has continued to exist, to move, to evolve. Where the galaxy actually is right now, in this present moment, is a separate question from where its ancient light shows it to be. For nearby galaxies like Andromeda, the difference is modest, because the gap between us is still small on cosmic terms, and the universe's expansion has barely stretched it. But the principle just introduced that the distance light has already travelled is not the same as the present-day distance to an object, is the seed of the strangest and most final barrier in the entire cosmos, and we will return to it with full force at the largest scale of all. Andromeda offers one more lesson before we leave it, a small mercy amid so many unreachable things. Because the local group is held together by gravity, its galaxies are not flying apart from one another, they are bound, and Andromeda, remarkably, is not receding from us at all. It is falling toward us, drawn by our mutual gravity, closing the gap at around 400,000 kilometers per hour. For decades, we assumed the two would surely collide and merge within about 4 billion years, but recent studies, weighing the uncertainties more carefully, have downgraded that fate from a certainty to something genuinely in doubt. This is the rare case where a distant cosmic object is not slipping away from us but coming closer. It matters for what follows, because it marks the boundary of a kind of intimacy. Within the local group, gravity still wins. These few dozen galaxies are genuinely bound together, genuinely a family, destined to stay in contact, to mingle, even to merge. They are the last structures large enough to be called our neighbours and still remain, in the deepest sense, reachable in principle. But notice what even this bound family does to the idea of contact. 2.5 million light-years to Andromeda means that a message sent there, at the speed of light, takes 2.5 million years to arrive, and a reply 2.5 million years to return. 5 million years for a single exchange with the very nearest major galaxy, the friendly one, the one falling toward us, the one we are gravitationally married to. 5 million years ago, our ancestors had only just begun to walk upright. Whatever sent a greeting to Andromeda when our forebears first stood on two legs would still be waiting, today, for the answer to come home. Even within our own bound galactic family, even with the nearest neighbour we have, two-way contact is a fantasy measured against the whole arc of human evolution, and our local group, that bound family of galaxies, is far from the top of the cosmic hierarchy. It is merely the lowest rung of a ladder that climbs through structures so large they make even a galaxy seem modest. We could simply name those larger structures and move on. But that would betray the whole point of this journey, which has been to make each scale real, to feel the weight of every step rather than skip past it. The gulfs we are about to cross are not just wider than the ones before, they are wider by amounts that change what the word distance even means. So we will take each of the next steps with real care. Let us actually climb that ladder rather than wave at it, because the next rungs are staggering in their own right. Our local group, those 50-odd galaxies bound by gravity, sits near the ragged outskirts of a far greater assembly. Stretch your view across about 50 million light-years and you reach the Virgo cluster, a dense swarm of well over 1,000 galaxies, massive enough to gently tug on our entire local group from across that immense gulf. We are, in the slowest possible sense, falling toward it, And the Virgo cluster is itself merely the bright heart of something larger, still a structure called the Virgo supercluster, a sprawling collection of galaxy groups and clusters spanning roughly 110 million light-years, within which our local group is one minor, outlying member among many, yet even that is not the top of the ladder. In 2014, astronomers mapping the motions of thousands of galaxies discovered that the Virgo supercluster is only one lobe of a far vaster structure, and they gave it a Hawaiian name, Laniakea, meaning immeasurable heaven. Laniakea spans about 520 million light-years and contains the staggering total of roughly 100,000 galaxies, and our Milky Way lives near its distant edge. They defined this colossal structure not by drawing a line around it, but by tracing the flow of its galaxies, mapping which way each one drifts. Everything within Laniakea, our galaxy included, is slowly streaming inward toward a single gravitational hub deep within it, a concentration of mass so great it pulls 100,000 galaxies toward itself. We cannot even see this hub clearly, for it lies hidden behind the dust of our own galaxy's disk, and so it carries a fittingly ominous name, the Great Attractor. Hold the full sweep of the climb in your mind. The nearest stars made our solar system a speck. The galaxy made our whole stellar neighborhood a speck. The local group made our galaxy one of 50. And now Laniakea makes our entire local group a faint mote near the rim of a structure of 100,000 galaxies, all of us drifting together toward an attractor we cannot even see. At every rung, the thing we just called vast collapses into nothing against the thing above it. But here lies the crack that breaks the whole ladder open. Laniakea is not bound. Unlike our snug local group, this supercluster is not held together for keeps by its own gravity. It is already being pulled apart, its distant reaches being carried away from one another by the expansion of space, faster than the Great Attractor can ever gather them in. Laniakea is not a stable home. It is a fleeting pattern, a structure already in the slow process of being torn to pieces by the very thing we have not yet fully confronted, the expansion of the universe itself. And once that expansion takes center stage, distance stops merely outlasting us and starts forbidding us outright. Stack up what distance has taken from us as we climbed. At the solar system, it took the instant reply and the rescue. Between the stars, it took the human lifetime and demanded generations. Across the galaxy, it took the continuity of civilization, making any far exchange outlast the culture that began it. And now, reaching toward other galaxies, it takes contact itself even from our nearest and friendliest neighbor, stretching a single hello and answer across 5 million years of evolution. Every rung has removed something we depend on, the reply, the rescue, the shared lifetime, the shared civilization, and now the shared moment of contact across the void between galaxies. But through all of this, one assumption has survived, battered but intact. At every scale so far, the barrier has ultimately been one of time. The distances were monstrous, the durations beyond comprehension, yet in principle, with enough patience, enough generations, enough centuries piled on centuries, a traveller moving at the speed of light could eventually arrive. Light from Andromeda reaches us, so light from us could reach Andromeda. The journey would outlast everyone who ever cared about it, but the destination was still, in the strict logic of physics, gettable. Slow, lethal to any traveller, impossible for any civilization to coordinate, but reachable, if only by something willing to spend eternity getting there. That final assumption is the one the universe is about to revoke. Because as we push beyond our bound local group, beyond the supercluster, out toward the most distant galaxies our telescopes can find, we encounter something that makes every barrier we have met so far look almost gentle. Out there, space itself is not merely large. Space itself is growing, stretching, carrying the most distant galaxies away from us faster than any signal could ever chase them down. And once that happens, distance stops being a problem of time at all. It stops being a question of how long the journey takes. It becomes a wall that no amount of patience, no number of generations, no speed short of the impossible can ever overcome, a barrier where we can still see the destination perfectly, its ancient light still arriving night after night, while the destination itself drifts forever beyond the reach of anything we could ever send. To understand how the cosmos can show us a place and yet forbid us from ever arriving, we have to leave the realm of mere distance behind and confront the expansion of space itself. Push out past the local group, past the bound family of galaxies falling gently toward one another, and the character of the universe changes in a way that nothing at the smaller scales prepared us for. Up to this point, every barrier we met was, at its heart, a barrier of time. The distances were monstrous and the durations beyond comprehension, but the destination always remained, in the strict logic of physics, reachable slow, lethal, civilization defeating, yet gettable by something patient enough. Out here, beyond the gravitational grip of our local family, that final assumption quietly dies. Because out here, space itself is not merely vast, space itself is growing. And a growing universe does something that no gap between planets or stars or galaxies ever could. It turns distance from a problem of patience into a problem with no solution at all. First, see the shape of the thing we are now standing inside. Map the positions of galaxies across the largest scales. Plot them in 3 dimensions across billions of light years, and the universe does not look like a smooth scattering of points. It looks like a structure, a vast, branching, foam-like architecture that astronomers call the cosmic web. Galaxies are not sprinkled evenly through space. They gather along immense threads, filaments of matter that can stretch for hundreds of millions of light years, strung between dense knots where great clusters of galaxies pile up. And between those bright threads lie the voids, colossal, near-empty bubbles of space, some of them hundreds of millions of light years across, containing almost nothing at all. The matter of the universe clings to the walls and filaments of these bubbles, while the bubbles themselves, the true majority of all volume in existence, sit dark and hollow and silent. This is the real texture of the cosmos at the grandest scale, and it inverts everything our instincts expect. We picture space as full of galaxies. It is overwhelmingly empty, with the galaxies merely tracing the thin, bright edges around enormous wells of nothing. The spectacular objects, the clusters, the superclusters, the glowing walls of galaxies are the exception. The rule is the void. If the gap between stars was an emptiness that swallowed lifetimes, and the gap between galaxies an emptiness that swallowed civilizations, then the voids of the cosmic web are an emptiness on a scale that begins to swallow the meaning of travel itself. You could fall through one of these voids at the speed of light for tens of millions of years and pass nothing, no star, no galaxy, no warmth, only the slow stretching dark. And this architecture is not a passing arrangement, not a snapshot of one cosmic moment. It is the final shape that gravity has carved across nearly 14 billion years, the largest pattern that matter forms anywhere in existence. Every galaxy, every cluster, every supercluster we have climbed through is simply a brighter knot strung along these threads, and the threads themselves trace the slow, patient work of gravity drawing matter together, while the voids between yawn ever wider. When you look at the cosmic web, you are seeing the universe's deepest structure, the end state of all the gathering that distance permits, and all the emptiness it does not. And it is that stretching that we must now finally confront, because it is the engine behind the last and most absolute barrier in this entire story. Space is expanding. This is not speculation. It is among the most thoroughly confirmed facts in all of science, established nearly a century ago and refined relentlessly ever since. The galaxies are, on the whole, moving apart, and crucially, they are not flying through space like shrapnel from an explosion. The space between them is itself swelling, growing, inserting new distance everywhere at once. Picture dots painted on the surface of a balloon as it inflates. No dot is travelling across the rubber, yet every dot grows farther from every other dot, simply because the rubber between them is stretching. The galaxies are the dots, space is the rubber, and the universe has been inflating for almost 14 billion years. Here is the consequence that changes everything. If the space between us and a distant galaxy is constantly growing, then the distance to that galaxy increases over time on its own, without the galaxy going anywhere. And the farther away a galaxy is, the more space lies between us, and so the more total stretching happens. and the faster that galaxy's distance grows. Double the distance, and you double the rate at which the gap widens. Push far enough away, and you reach galaxies whose distance from us is growing so fast because of all the cumulative stretching of all the space in between, that the gap widens faster than light itself could ever close it. Let that land carefully. There are galaxies in the universe right now whose distance from us is increasing faster than the speed of light. This breaks no law of physics, because nothing is moving through space faster than light. It is space itself, in its sheer accumulated quantity, that is growing. But the result for us is merciless and final. If you sent a beam of light towards such a galaxy today, the fastest possible message, the fastest possible anything, that light would never arrive. It would fly outward forever, and the space ahead of it would stretch faster than it could cross, and the galaxy would recede ahead of the beam for all eternity. No signal we send today can ever reach it. No ship, no probe, no message, no matter how fast, no matter how patient, no matter how many billions of years we are willing to wait. The destination is not far, in the sense that the stars were far. It is gone in a way that no amount of time can repair. This gives us a boundary unlike any we have met. Astronomers call it the cosmic event horizon, and we must define it precisely, because this is exactly the kind of place where loose language ruins everything. The cosmic event horizon is the line that separates the galaxies we could still, in principle, reach or signal from the galaxies that are forever beyond our touch. It sits at a present-day distance of roughly 16 billion light-years. Everything inside that horizon we could, given impossible spans of time, still send something to. Everything beyond it is sealed away from us permanently, not by its distance alone, but by the expansion of the space in between, which guarantees that nothing we ever do can close the gap. 16 billion light-years marks the true edge of our reach. It is the boundary of what physicists sometimes call the reachable universe. Now here is where you must keep two ideas rigidly separate, because almost everyone collapses them into one and loses the entire meaning. The cosmic event horizon, the limit of what we can reach, is not the same thing as the edge of what we can see. These are two different boundaries at two different distances, and confusing them turns this story into nonsense. What we can see is bounded by a different line entirely, called the particle horizon, and it lies much farther out. Because the universe has a finite age, about 14 billion years since the Big Bang, light has only had a finite time to travel toward us. The most distant light we can possibly detect is light that has been travelling the entire age of the universe to arrive. But remember the lesson Andromeda taught us. The space that light crossed has been stretching the whole time it was in transit. So although that ancient light has been travelling for 14 billion years, the objects that emitted it have, in the meantime, been carried by expansion to a present-day distance of roughly 46 billion light-years. That sphere, about 46 billion light-years in radius, 93 billion across, is the observable universe. It is everything we can see. So hold the two numbers side by side and feel the gap between them. We can see out to about 46 billion light-years. We can reach only out to about 16 billion. And in the space between those two horizons lies the most quietly devastating region in all of physics, a vast shell of galaxies that we can see perfectly well, whose light pours into our telescopes night after night, and which we can never, under any circumstances, reach or contact or affect in any way for the rest of time. Think about what that means concretely. Out there, beyond 16 billion light-years but within 46, are countless galaxies, billions of them shining in our images, mapped, catalogued, their colours and ages recorded. We know they are there, we can point to them, and every one of them is already gone to us. A message sent toward them today will never arrive. A ship launched toward them today, even at the speed of light, will fall behind the stretching of space and drift forever without reaching them. We are looking at the light of places we are permanently forbidden to visit, and worse. In many cases we are looking at light those galaxies emitted long ago, while the galaxies themselves have since crossed beyond even the horizon of things we will ever see in their present state. The cosmos lets us chart the route in perfect detail, and then seals the road. The numbers here are not gentle. When you account for the full geometry of the galaxies we can see but can never reach, The overwhelming majority of the observable universe is already out of our grasp. By widely cited estimates, something on the order of 94% of the galaxies we can currently see are already beyond the cosmic event horizon. They are visible and unreachable at the same time. Of all the galaxies whose light reaches our eyes, more than 9 in 10 are places no signal from Earth, sent today, will ever touch. We can study almost the entire visible universe. We can travel to almost none of it. The fraction we could ever actually reach is a small, bright core, surrounded by an immense halo of the permanently lost. And this barrier is not holding still. It is closing in. To understand why, we have to name the force behind the acceleration, the thing that makes distant space stretch ever faster, a presence astronomers call dark energy. It is, by every measurement we can make, the dominant component of the entire universe, accounting for roughly 68% of everything that exists, far outweighing all the matter, all the stars and gas and dark matter combined. Yet we can barely say what it is. It appears to be a property of empty space itself, a faint outward pressure woven into the vacuum, and its defining feature is relentless. As space expands, dark energy does not thin out or weaken. Every new cubic meter of space comes with its own measure of this outward push. So the more the universe expands, the more total dark energy there is to drive it, and the faster the expansion becomes. It was the discovery of this acceleration, in 1998, through the careful study of distant exploding stars, that revealed dark energy's existence and overturned the old assumption that cosmic expansion must be slowing down. Here is the consequence that should chill you. Because the expansion is accelerating, the cosmic event horizon, that 16 billion light-year boundary of everything we could ever reach, is not fixed. It is shrinking. Slowly, inexorably, galaxies that lie just inside the horizon today are being carried across it, passing from the reachable column into the unreachable one. And once they cross, they are gone to us forever. We are not merely separated from most of the universe. We are being separated from more of it with every passing moment. The pool of galaxies we could still, in principle, send something to is draining away, one by one, as the acceleration sweeps them beyond the line. There is no malice in it and no drama. The galaxies do not appear to move. They simply recede a little faster each age, until the day comes when the gap between us and them grows faster than light can cross, and the door quietly closes. Every galaxy, currently sitting near our event horizon, is a galaxy we are, in this very era, losing the last chance to ever reach. Distance, at this scale, is not a fixed wall we might one day learn to climb. It is a tide going out, and everything it carries past the horizon, it carries away for good. And distance is not content merely to take away our reach. Given enough time, it comes for our sight as well. Remember that the light from receding galaxies is stretched by the expansion of space, as it travels its waves pulled longer and longer, shifted toward the red and then beyond, into wavelengths our eyes and even our instruments struggle to detect. The faster a galaxy recedes, the more violently its light is stretched. For the galaxies being swept toward the event horizon, this stretching grows without limit. Their light does not simply dim with distance in the ordinary way. It is drawn out, redshifted toward oblivion, its energy bled away until the signal sinks beneath anything we could ever hope to capture. Picture a voice calling to you as its owner walks away into a vast darkness. At first the words are clear, then, as the distance grows, the pitch seems to drop, the sound deepening and slowing, the words smearing together, fainter and lower with every step, until the voice falls below the lowest tone your ear can register, and is simply gone, not silenced suddenly, but stretched into inaudibility. This is what expansion does to the light of the most distant galaxies. One by one, over immense spans of time, they will not wink out but fade out, reddening and dimming until they slip past the edge of detectability and vanish from our view entirely, even though they are still there, still shining, somewhere far beyond our reach. So the great shell of galaxies we can see but never reach is not even permanent in its visibility. It is a temporary gift. The cosmos shows us these unreachable places now, in this era, while their ancient light still arrives, but it is slowly drawing the curtain. First distance took our ability to go to them. Then it began taking our ability to see them at all. The view itself, the one consolation we thought was secure, turns out to be something the expanding universe is quietly, permanently taking back. And it is essential to be clear about what this is not, because the truth is strange enough without exaggeration. This does not mean the universe has a wall. The observable universe is not a physical edge. It is simply the distance light has had time to cross. Beyond it, space almost certainly continues, likely far, far larger than what we can see, possibly without end. The boundary is in us, in our vantage point and the finite age of the cosmos, not in the universe itself. Nor does expansion mean that everything is being torn apart everywhere. This is the other great misconception, and it is wrong. Inside galaxies, inside the local group, inside any region where gravity is strong enough, the expansion does not win. Our galaxy is not stretching. The local group is not flying apart. Andromeda, as we saw, is actually falling toward us. Gravity holds the local structures together. Expansion only dominates on the largest scales in the great gulfs between distant galaxies that are not gravitationally bound to one another. The Earth is not growing. The Sun will not be stretched away. Your atoms are safe. What expansion governs is the relationship between distant, unbound islands of matter, and there, on those scales, it rules absolutely, which means the barrier we have reached is not loud or violent. There is no catastrophe, no rending, no visible line in the sky. The galaxies beyond the event horizon look exactly as serene and beautiful in our images as any others. The wall is utterly silent, written into the geometry of space itself, and it separates us from the majority of everything, not with fire, but with simple, irreversible distance. Follow that process to its end, far into the future, and you arrive at one of the strangest and loneliest visions in all of cosmology. There is a number that captures the outer limit of everything we will ever be able to see, a future visibility limit of about 62 billion light-years, which is simply the 46 billion light-years we can see today, added to the 16 billion we could still reach. It marks the absolute farthest extent of the cosmos that will ever become visible to us, the final boundary of our knowledge, beyond which nothing will ever come into view no matter how long we wait. The universe has not only walled off most of itself from our touch, it has set a hard ceiling on how much of itself it will ever allow us to even glimpse, and within that ceiling, the visible contents are draining away. Run the clock forward billions upon billions of years. The galaxies beyond our gravitationally bound neighborhood recede, redden, and fade, slipping past the horizon of sight one after another. Meanwhile, our own local group, the Milky Way, Andromeda, and their dozens of small companions remains bound by gravity, immune to the expansion, and over time these galaxies will draw together and merge into a single vast island of stars. Eventually, that merged galaxy will be all there is to see. Every other galaxy, every distant cluster, the entire glittering cosmic web will have receded beyond both reach and sight, their light stretched into nothing. Now imagine astronomers arising on some world in that far future galaxy. After the rest of the universe has vanished, they look up and they see only their own island of stars, surrounded by perfect, total darkness in every direction. They have no distant galaxies to observe, no receding light to measure, no evidence whatsoever that space is expanding or that anything exists beyond their single galaxy. From everything their instruments could ever detect, they would be forced to conclude that their galaxy is the entire universe, alone and unchanging in an infinite void. The truth that the cosmos was once filled with 2 trillion galaxies, that it began in a great expansion, that it is still flying apart would be utterly invisible to them, erased by the very expansion that caused it. The deepest facts about the universe would have become permanently unknowable, not through any failure of intelligence, but because distance had carried the evidence away. We, by sheer accident of timing, live in a brief and precious window when the universe still reveals itself, when the distant galaxies are still visible, when their light still carries the story of an expanding cosmos, when we can still see far enough to know what is happening. Those future astronomers will inherit only silence and a single lonely galaxy. The cosmos is not only taking the distant universe away from us, it is, on a long enough timescale, taking away the very possibility of ever knowing it was there. And so even knowledge itself, the last thing we imagined distance could never touch, turns out to have an expiration date written into the expansion of space. Step back now and look at the full shape of what distance has done across this entire journey, because the pattern is the point, and it has been building from the very first frame. Down in the solar system, distance took the instant reply. A command to Voyager arrives a day late, a conversation becomes a 2-day exchange, and the rescue, as Apollo 13 learned, was already impossible even when the radio still worked. The first thing the cosmos removed was the back and forth, the immediate help, the ability to react in time. Out among the stars, distance took the human lifetime. The nearest star lies beyond the reach of any life that could decide to go. Even our fastest probe would need 73,000 years to arrive, and crossing the gap demanded either a chain of generations who would never see the launch and the landing as the same people, or a technology we have only sketched. The journey stopped fitting inside a life. Across the galaxy, distance took the civilization. A message to the galaxy's far side and back consumes 200,000 years longer than our species has existed in its modern form, so no culture could send a question and survive, unchanged, to hear the answer. We could photograph the whole galaxy and never cross it, never coordinate it, never hold a single living conversation across it. Between the galaxies, distance took even contact with our nearest neighbour. A hello to Andromeda and its reply span 5 million years, the whole arc of human evolution, even though Andromeda is the friendly one, the bound one, the galaxy falling toward us. And here, at the largest scale, distance takes the last thing it had left us, the destination itself. Not the reply, not the lifetime, not the civilization, not the contact, but the very possibility of arrival. For most of everything that exists, the expansion of space converts the majority of the visible universe into a place we can see and never reach, a country shown to us in full and sealed against us forever. Notice that at no point in this entire ascent did the universe ever attack us. There were no monsters, no hostile worlds, no killing radiation that defined any of these barriers. We have not been speaking of dangers. We have been speaking of distance, and distance alone, the simple, silent fact of how far apart things are, and we have watched it strip away, one rung at a time, every single thing we depend upon when we reach towards something far away. The reply, the rescue, the shared lifetime, the shared civilization, the chance of contact, and finally the chance of arrival. Each scale did not merely add a bigger number. Each scale removed another assumption, until the only thing left to remove was the destination itself. This is the realization the whole journey has been carrying toward, and it deserves to be said plainly. The deepest barrier in the universe may not be radiation, or the cold, or the lack of a fast enough engine, or the hostility of distant worlds. The deepest barrier is separation itself. It is the thing the cosmos enforces for free, without effort, without malice, simply by being as large and as expansive as it is. We spend so much of our imagination on the dangers of space, the things that might hurt a traveller, the worlds that might be unkind. But the truly insurmountable thing was never a danger. It was the gap, the emptiness, the growing dark between one island of warmth and the next. Nothing has to threaten us for the universe to keep us apart. It only has to be vast, and it is vast beyond any threat we could imagine. And yet, and this is the strange grace woven through all of it, the same universe that forbids us the journey, grants us the view. This is the quiet paradox at the heart of everything we have traced. The cosmos is miserly with arrival and astonishingly generous with sight. It will not let us cross to the nearest star within a lifetime, but it lets us see that star with our naked eyes every clear night. It will not let us reach Andromeda, but it lays Andromeda's 2.5 million-year-old light gently onto our retinas for free, a whole galaxy delivered to a dark backyard. It will not let us touch the billions of galaxies beyond the event horizon, but it floods our telescopes with their ancient light, lets us count them, measure them, learn their histories, even as it holds them eternally beyond our reach. We are permitted to behold almost the entire universe, we are permitted to enter almost none of it. There is something almost unbearable in that arrangement, and something almost beautiful. We are creatures who can map a cosmos we can never traverse, who can hold the image of 93 billion light-years in a single mind, while being bound, in body, to one small wet rock circling one ordinary star. The light of unreachable places falls on us anyway. The portrait of forbidden countries is hung in our sky, freely, nightly, whether or not we ever look up. Distance has taken everything else we had leaned upon as we slowly climbed through these widening scales, and yet it leaves us this one thing it cannot take. It leaves us the seeing. It leaves us the knowing. So when you stand outside tonight and find that faint smudge of Andromeda, or simply let your eyes rest on the scattered stars of our own small arm of the galaxy, understand exactly what you are doing. You are looking across distances that have already swallowed lifetimes and civilizations, and the very possibility of return. You are receiving light from places you will never go, that no one will ever go, that the expanding universe has sealed away for all of time, and you are seeing them anyway. The cosmos shows us a country we are not permitted to enter, shows it to us in full, in detail, in light older than our species, and asks us to make our peace with looking. The distance in space is more horrifying than you think, not because it is large, but because of everything that largeness quietly takes. And it is more wondrous than you think, for the single reason that, across all of it, the light still finds its way to our eyes. We cannot cross the universe, but the universe, in its strange and silent generosity, still crosses itself to reach us and lets us see the very places it will never let us go.